Then we define the V0 as the union of all V0n. It can be interpreted as X1 cap all external boundaries of Vn. So, to recognize this distillation, I propose some examples. So I will show you some photo of distillations. So the first is the one-dimensional case. The root is 0. And then the bracket at 0 is 0, 1, and minus 1. Bracket at 2, 1. So elements of V0 are even numbers. So then we pass to the square lattice. For the square lattice, we have the following distillations. Here is 0, 0. And the bracket at 0 is given by this. And then we define other brackets. It's clear that in blue are elements of V0, the center of brackets. Clearly, there is no edge joining centers of brackets, but their brackets may have an intersection. This is the key point, is that the centers of brackets are not joining through edges. And then, for the case of the Cayley tree for the two, the first, or the semi-infinite Cayley tree, the first root is, or the root is Y0, then we define other brackets. Here also, it's clear that the centers of brackets are not interacting directly with edges. So, for another little bit complicated graph, we may fix tessellation also. Once we choose the root, the tessellation is fixed, because the unique artificial thing is the choice of this root. Other things are fixed by this choice. So, sorry, I have a lot of problems inside my laptop. So then we pass to the construction of conditional density operators in order to define quasi-conditional expectation. Given a family of operators belongs to AXY, with AXY is the tangent product of AX by AY, and XY is an edge. Satisfying these two conditions, KXY is invertible, and this is star algebra generated by KXY and K star XY for Y in V0, the set of all centers of brackets, and V0, and NY is the bracket. We assume that this algebra is commuted. Then we define the following operator. The NY is the phi conditional expectation on Y applied to the square of this operator. Then we may prove that the NY is invertible. Moreover, it belongs to the commutator, to the commutant of K. Then we define the following operator. The following operator is the conditional density amplitude of phi on 1. This This operator is defined over the algebra generated by the bracket, but it's the conditional amplitude just for y. So we do not need the phi conditional expectation over the bracket. We need only the conditional expectation over y to get conditional density amplitude, and this is very interesting with respect to the tessellation. Then we propose a first construction. We define the boundary of a given subset with respect to V0 as the union of elements of the boundary of lambda, here cap V0. Okay? Cap V0 means the centers of brackets of the brackets. So then we give the following operator for any finite subset lambda. We have the following property for disjoint path, here lambda 1 and here lambda 2. So, and then we get the following limit. Define phi lambda as phi 0 of k star lambda k lambda. Then you give the following result. This net converge where lambda go to V in the Wake-Star topology. Moreover, the limit satisfy this property. The restriction of phi over a lambda is phi lambda bar of over a lambda. So without using the tessellation, even in the one-dimensional case, this result is in general one. Without using the tessellation, we cannot find the limit even in the one-dimensional case. So the tessellation here play a crucial role. So now we pass to the next construction of the second. It's quite difficult. It's quite different to the first one. In this construction, we propose a total order. So the result depends on this order. So we may check that this set is finite. So we take its cardinality Dn, and we may denote it as follows. Then we consider the following total order over the external boundary of Vn. We have this order. We propose this order, and for y and z in different levels, if the level of y is indiced by an integer less than that one of z, automatically y is less than z. So using this total order, we may get in substance the analog of the one-dimensional case, of course through the tessellations. Then for a given y, we define the following part, the following parts of V.